All right, so probability. This section's, I think it's fun. We'll see if you guys think it's fun. It's really useful for like card games and like dice games and things like that. And if you're not a gambler, it's good for Yahtzee. Yahtzee is a game with, I think, 5 dice, and you roll them all at once and try to get different combinations. All right, so we're going to talk about probability. Whenever we talk about probability, typically we think about stuff of, oh, you've got a 50% chance of winning, or you have a 20% chance of winning, or whatever. But this percent, you guys know you can take it to a decimal, right? So 50% would just be 0.5. Okay, so your probability, when we talk about the probability, we're going to use it in decimal form. It's the same idea as the percent, but we're making it a decimal. So you can only be between 0 and 1. You can't have a negative probability that anything's going to happen. I don't even know how to define that. So it just can't happen. You can't have a negative probability. And also you can't have more than 1. So whenever people say that they're 110% certain that, no. If you know for sure it's going to happen, you're 100% certain it'll happen. So you have a probability of 1. If you know for sure it will not happen, it has a 0% chance of happening, or a probability of 0. So we're going to leave out all those really nice slogans of, it's 120%. No, we don't. Not for us. So between 0 and 1. One of the big things to note here is if you're doing a problem and you get a probability that is bigger than 1, you did it wrong. And if you get a probability that's negative, you did it wrong. And I say that because on the test somewhere, hopefully make a liar of me, but on the test somewhere, somebody will say that there is a 1.26 probability that you will roll 3 5s or something like that. Not the case. So again, make sure that your probabilities are going to be between 0 and 1. All right, so figuring out your probabilities isn't hard. So whenever we flip a coin, you guys like just intuitively know there's a 50%, yeah, it's a 50-50 shot of getting a head or a tail. So if we wanted a head, so of the 2 possible outcomes, right, there's only 2, you can only have a head or a tail. So the probability of getting heads on 1 flip, well, the number of things that you want to have happen out of the number of possibilities. And this is actually going to be our theoretical idea. So, because in theory, we can think about there's 2 possible outcomes, there's 1 we want. The first page is empirical probability. So this is where they actually give you the numbers. So if they said, I flipped a coin, I got heads 7 times, and I got tails 9 times. And they give you this. They say, what's the probability of getting heads? And they're telling you to compute the empirical probability. Well, if you want the number of heads, that was 7 out of your total. You flipped the coin how many times? Yeah, 7 plus the 9, so 16 in total. So you actually flipped it 16 times, and you got heads 7. So using empirical, which is going to be your observed probability, so think experiment, empirical, experiment, both start with EX. So this is what you actually observed during an experiment. Anyway, so it could be different, because if it was what we would calculate, then it would be, the probability of getting heads would be 1 out of 2. But empirically, so based on observation or experiment, it's going to be 7 out of 16 for the example I just gave. It would be different every time. So far, so good? All right, super. Okay, so we have this great chart here. I want to point out several things. So this is the marital status of people 15 or older in 2010. It's in millions. We don't really care that it's in millions because they're all in millions. And we're going to be putting a number over another number. So basically the millions would cancel out anyway. This is a really nice chart because it has totals going down the right side and across the bottom. So has never been married. If it just says has never been married, it means out of the entire survey. So out of all the people surveyed. So out of all the people surveyed, how many is that? The 242 is the total. Yeah. So there's the total, and then there's 74 that have never been married. It's a bad 7. And then we would reduce that down. All right, so 37 over 121. Is that between 0 and 1? Yeah, that's between 0 and 1. Super. Thank you. So 0.306. It could be either. So you'll have to read the directions and see what they ask for. A lot of times they will ask for the fraction. They'll say give a reduced fraction, or sometimes they'll say give a decimal to however many decimal places. But we could say either. So the probability that a randomly selected person has never been married is 37 out of 121, or has a probability of 0.306. You can say it either way. And we know that means a 30.6% chance, but we're always going to have the probability being between 0 and 1. All right, so the probability that they're male, what's my top number? Yeah. All right, so this is out of everybody. Is male. We're just on the is male now. So is male, you want all these people. So all the men's going to give you this 118. And then out of how many? Yep, 242. 148? That, did I write it right? Okay, super, thank you. All right, and then a widowed male. So we're looking for widowed men. All right, just 3 of those, and out of what's the total? Yeah, 242. Which is a tiny decimal, right? Here's a decimal in there. All right, those are okay? All right, super. All right, D, tiny little trick to it. It says among those who are divorced. Whenever it says among those who are divorced, it's saying, just look here. So we're ignoring everybody else. So of those who are, among those who are divorced, find the probability of selecting a woman. Yeah. So 14 over 24. And then for about 0.583. Okay, super. All right. So it says among the women, find the probability of selecting a married person. I want you guys to try that one real quick. All right, so among the women, find the probability of selecting a married person. So among the women, what's your bottom number? 124. Nice, 124. Because that means among the women, you're just looking here. All right, and then the probability of selecting a married person, what's your top number? Yeah. All right, that okay? All right, so we're going to talk about theoretical probability. So any occurrence for which the outcome is uncertain is called an experiment. The set of all possible outcomes is called the sample space. So if you're flipping a coin, your sample space would be heads and tails. Those are your only 2 options. And flipping the coin itself would be an experiment. All right, so an event's a subcollection or subset of a sample space. All sounds really horrible. This really isn't that bad. So theoretical probability, the number of outcomes in event E, divided by the number of outcomes in the sample space. So the number of outcomes that you wanted divided by the total possible outcomes. So whenever we're talking about the sample space, this is all the possible outcomes. So this is where we went and figured out the probability of getting a heads is 1 out of 2. Same idea. So here, they're nice enough to go ahead and give you the sample space. So it's a fair coin is tossed 2 times in succession, so 2 times in a row. And here's your sample space. So heads, 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 tails, tails, heads, and tails, tails. So that's all the possibilities if you flip a coin twice. So find the probability of 2 heads. How do we find that? Yeah, just 1 out of 4. So the probability of getting 2 heads, there's only 1 of those, and there's 4 things in the sample space. All right, you guys do B real quick. So find the probability of the same outcome on each toss. All right, what was your original unreduced fraction? Yeah, 2 out of 4, because you had heads, heads, so we had this one. We also are now adding tail, tail for having the same outcome. So 2 out of 4, and then that's going to reduce down to, yeah, 1/2, and we want a decimal, yeah. Those okay? Yeah, all right. All right, I'm going to let you guys go ahead and try 2. So you have a sample space for 3 children, and we're just discussing if they're male or female. So they've given you the sample space. They want you to find the probability of at least 1 male, and then find the probability of at least 2 females. All right, so the probability of at least 1 male is going to be what? Yeah, 7/8. So you can go through and you can count all the ones that are male, or have at least 1 male in them, which is everything but all female, right? So you've got 7 out of a possible 8 outcomes. I want you guys to also to realize, so probability of at least 1 male plus the probability of no males is going to be 1. Do you guys see that? Okay. So the probability of something happening and something not happening will always add to 1. We could have, so the probability of at least 1 male plus the probability of no males. And are you guys okay that how those are opposites? Okay. So that's going to be equal to 1. So that was 7/8 plus 1/8 equals 1. So what we could have done, if we wanted to solve for the probability of at least 1 male, if we subtract the probability of no males, yeah. So it wasn't too hard on this one, but we could have actually gotten the probability of at least 1 male being 1 minus the probability of no males. So it would have been quicker to count, right? Would have been quicker to count the 1 that was no. All right. I'm making a point for the next page, in case you were wondering. Yeah, because sometimes it's just a nicer calculation to do 1 minus whatever you're not looking for. But these aren't too bad. All right, and then the probability of at least 2 female children. Yeah. It'll be whatever they ask for as far as decimal or fraction. So sometimes they will say a reduced fraction or a simplified fraction, and sometimes they'll say a decimal out to however many decimal places. All right, those okay? Yeah, super. All right, go ahead and try number 3. So this is basically just giving you the sample space. If you were to go through and roll 2 6-sided die, so a 6-sided die just means you've got the numbers 1 through 6. Here's all the possible pairings that you could have. So for the first one, they want you to figure out probability of getting 2 numbers whose sum is 4. And for the second, find the probability of getting 2 numbers whose sum is 7. All right, so to find the probability that their sum is 4, first you've got to go through and figure out where your sums of 4 are. So we just have those 3. So what was your fraction before you reduced it? Yeah, 3 out of 36. And that reduced down to, which is about, all right, that one okay? Super. All right, probability that your sum is 7. So let's go find our 7s. Yeah, 6 out of 36. Oops, I actually went through that one. It's okay. So 6 out of 36, which reduces to, which is about. All right, those okay? See, probability is not bad. Okay, so here's what I was trying to kind of get you guys thinking about before we got here. So the probability of something not happening is 1 minus the probability that it will happen. Because the probability that it happens or doesn't happen always has to be 1. You've got a 100% chance that either it will or it won't. I know my mom was giving directions to somebody, and to get to my parents' house, there's a cow field that you have to pass. So she's telling them about the cow field. She's like, so you'll turn left at the cow field. And she's like, sometimes there's cows in there, and sometimes there's not. So, of course, we laughed, because, of course, there would either be cows or there wouldn't be. Just like the door is open or it's closed. You're here or you're not. The same idea. Anyway, so there's always a 100% chance of that or not that happening. Okay, so for number 1, a randomly selected person described in the table, which our table is educational achievement, the United States for people ages 25 and over. For a randomly selected person described in the table, find the probability that a person has not completed 4 or more years of college. So if they have not completed 4 or more years of college, then we would have to go through and figure out for those other 3 columns. You guys see that? Yeah, those first 3. Because less than 4 years of high school, 4 years of high school, some college, all of those qualify for the not 4 years or more of college. So the probability of not 4+ years is the same. We could, or we could just do 1 minus the probability of 4+ years. So this is going to turn out the same. We're going to work it both ways for this one, just to prove it to you. Because Charles came up with the great idea of, well, we just add them, right? So if you haven't done the 4 or more years, then you're going to be in these 3 columns. So if you can be in these 3, then the total that you're looking for is going to be this 29, this 56, and this 44. So this is the long way. Here, we'll do the long way in red. Okay, so what we're interested in is the 29, the 56, there we go, and the 44. And all that is out of, yeah, the 174. So our total. We add all that up. $129. All right, and then 129 out of 174 is about what? Point what? 0.741? All right. So here's the longer way where we can go through and add up all the categories we're interested in. Or we'll try it the other way. So the shorter way would be exactly the 1 minus the probability that they did attend 4 or more years of college. So what's that fraction look like? Yep, 45 over 174. And that's going to give us about what? Yeah. And again, either way is going to get you the same answer. And with this particular problem, it's not that much more work to do it the long way. It's whenever you get like super huge tables that it becomes a big deal. Or on that dice problem. So if I had said, what's the probability that you did not sum 2? Well, you could go through and add up the 35. Know that you got 35 out of 36, or it could just be 1 minus whatever was 2, which is just that one part, so 1 minus the 1 out of 36. So in that instance, if you're going to go through and count, it would be faster to do it the 1 minus way. All right. You guys try B. All right, let's try 2. 2's easier. First off, so here's a deck of cards. If you're not familiar with cards, with a deck of cards, get familiar with them. So a deck of cards, there's 52 cards. You've got 4 suits. 2 of those suits are red and 2 of those suits are black. You're going to have hearts, spades, diamonds, and clubs. And you've got 1, which is your ace, through 10. So there's your numbers, 1 through 10. And you've got jack, queen, king in that order. So it's either, depending on how you're counting your ace, because aces can be high or low. So ace through king would be a proper order, or 2 through ace. So ace can be even higher than a king, depending on how you're playing it or what game you're playing. Okay, so here's a perfect example where it's going to be way easier to do the 1 minus. So the probability that you are not dealt a king. First off, let's figure out the probability that you are dealt a king. Yeah, 4 out of 52. So the probability of not a king is the 1 minus the probability of a king, which is going to be 1 minus, and you guys told me 4 out of 52, because there are 52 cards total, and each suit has a king, so there's going to be 4 kings. So that's going to get us down to 12 over 13. Which is what? Thank you. So about 0.923. All right, I want you all to try B, so that you are not dealt a pitcher card. Pitchers being jacks, queens, and kings. All right, so first off, you guys agree that the probability that it's not a pitcher is the same as 1 minus the probability that you did get a pitcher card. I'll assume you all said yes. All right, so the probability of getting a pitcher card, how many pitcher cards are there?
12.
Yeah, 12 out of 52. And if we subtract and reduce that down, what do you get? That's okay, so 0.769. All right, you could have also gone through and figured out, you could have counted all the 1 through 10 and done the same thing and still gotten there. It just would have been a little more work. Mm-hmm. Will you always have a picture of the cards? No. Yeah, you guys need to become familiar with a deck of cards. They're useful. It is good to know. I won't give you anything that's crazy, anything harder than the cards as far as expecting you to know it. So like I would expect you to know that flipping a coin, you can get a head or a tail. Having a kid, you can get a male or a female. I know there's more options, but we'll assume those are the only 2. Things like that.
All right, let's talk about probability with mutually exclusive events. So a mutually exclusive event, that means that both things can't happen at the same time. For instance, you can't be a male and a female at the same time, or you can't be employed and not employed at the same time. You're either one or the other. Sometimes things are not mutually exclusive. That's going to be whenever you can be 2 things at once. So you can be female and employed at the same time, or you can be male and unemployed at the same time. So we're going to talk about how to find the probability of or events whenever they're mutually exclusive or whenever they're not mutually exclusive. So for our first example, you're dealt a red 7 or a black 8. So we're trying to find the probability of a red 7 or a black 8. Well, because you cannot be a red 7 and a black 8 at the same time, these are mutually exclusive events. So we can just add the probability of each. So we have the probability of being a red 7 plus the probability of being a black 8. And if we look, we have 2 red 7s. So we have a 7 of hearts and a 7 of diamonds. So that's going to be 2 out of 52. Plus, in the probability of a black 8, we have 2 black 8s. We have the 8 of clubs and we have the 8 of spades. So that's going to also be 2 out of 52, which gives us 4 out of 52. And this will reduce down to 1/13. So the probability of being dealt a red 7 or black 8 is 1/13. Okay, now it says the probability that you were dealt a 7 or a red card. Well, here, these are not mutually exclusive. It is very possible to be a 7 and a red card. So we're going to first do the probability of being a 7. We're going to add the probability of being a red card. And then we'll need to subtract the probability of being a red 7. So being both 7 and red. So the probability of being a 7, there's 4 7s out of the 52 cards. So 4 out of 52. Plus the probability of being red, well, we have 2 suits that are red, the hearts and the diamonds. So that's going to be 26 out of the 52 cards. And then we're going to subtract out the red 7s. Well, we have 2 red 7s. We have the 7 of hearts and the 7 of diamonds. So we're going to subtract the 2 out of 52. And in total, that's going to get us to 28 out of 52, which will reduce down to 6 out of 13. Now, to go and look at this a little bit further, if we look at our 7s, so here's our 7s, and there's our 4 7s. So we added that here. So there are the 4 7s. Well, we also added all of our red cards. So here's all of our red cards. So there's 13 there and 13 here. So here, the 13 plus 13 gives us the 26 out of 52. What we're subtracting is that overlap that we have because we've counted those 2 times. So since we've counted the red 7s twice, we have to subtract out that overlap. So we're subtracting the overlap right here. All right, for number 2, we're going to find the probability that the pointer will land on an odd number or a number less than 6. Well, these are not mutually exclusive. You can be odd and less than 6. So we need to find the probability of being an odd number, add the probability of being a number less than 6, and then subtract the probability of being an odd number that's less than 6. So the probability of being an odd number, on our spinner, we have the numbers 1 through 8. So we know that our sample space is 8, or the bottom number, the denominator, is 8. The number of odds we have 1, 3, 5, and 7. So that will be 4 of them. And then we need the probability of being less than 6. Less than 6 does not include 6. So that's only going to include the 5, 4, 3, 2, and 1. So that will be 5 out of 8. And then we need to subtract out the odd numbers that are less than 6. So the odd numbers less than 6 will be 5, 3, and 1. So there are 3 numbers that are odd and less than 6. Now, whenever we go through, we're going to have our 4 8s plus 5 8s, which gives us 9 8s, minus 3 8s gives us 6 8s, and this will reduce down to 3/4. If you prefer a decimal, we can do 0.75. Now, I want to make a note here. if you did not realize that these were not mutually exclusive. So if you did not realize you're going to have to subtract out the overlap or the numbers that got counted twice, whenever you look here, this should have been your clue. If you had stopped after only adding the odds, or the probability of being odd and the probability of being less than 6, you would have ended up with 9/8, which is a number bigger than 1. You cannot have a probability bigger than 1, so that would have been your clue that you did something improperly. All right, now using our spinner again, let's find the probability of an odd number or a number greater than 3. So we need the probability of odd plus the probability of a number greater than 3, and then we need to subtract out the probability of being odd and greater than 3. Because it is possible to be both, these are not mutually exclusive, so the probability of being odd is still 4/8. The probability of being greater than 3, that's going to count 4, 5, 6, 7, and 8, so that's going to be 5/8. And then we're going to subtract out the odd numbers greater than 3. That's only going to be 5 and 7. So we're going to subtract 2/8. Whenever we go through and simplify this, we're going to end up with 7/8 for our answer. Or, again, if you prefer decimal, 0.875 for your probability. Okay, let's do one more. So a mathematics department of a college has 8 male professors, 11 female professors, 14 male teaching assistants, and 7 female teaching assistants. Find the probability of selecting a random person who is a professor or a female. Well, obviously, you can be both a professor and female. Since they are not mutually exclusive, we'll need to do the probability of being a professor. We will add the probability of being a female, and we will subtract the probability of being a female professor. We have 40 people in total listed, so the probability of being a professor, well, we have 8 male professors and 11 female professors, so we have 19 out of 40. For the probability of being a professor. The probability of being a female, we have 11 female professors and 7 female teaching assistants. So we have 18 females. So 18 out of 40. And then we need to subtract the probability of being a female professor. And it tells us that there are 11 female professors. So whenever we go through, we're going to end up with 26 out of 40, or 13/40. And this is equal to 0.65 if you prefer decimal. All right, now let's do the same thing to find the probability of selecting a professor or a male. So we're going to, again, do the probability of picking a professor plus the probability of being male, and then we're going to subtract the probability of being a male professor. The probability of being a professor is going to remain 19 out of 40. The probability of being male, we have 8 male professors and 14 male teaching assistants, so that will be 22 out of 40. And then we're going to subtract the male professor, so we're subtracting 8 out of 40. So this will give us 33 out of 40, which is equal to 0.825. All right, now let's talk about probabilities with independent events. So what this means is that you want a series of events to occur. For instance, the first example is rolling a single 1 die, so a 6-sided die, and find the probability of rolling a 5 the first time and then a 1 the second time. Up here, it says that we're going to take the probability of whenever we're doing and, we're going to take those probabilities and multiply the probabilities. So the probability of getting a 5 the first time is going to be 1 out of 6. It's a 6-sided die, so there's 6 possible outcomes, and we're only interested in getting a 5. So we're only interested in one of the outcomes the first time. And then rolling a 1 the second time. Again, the probability of rolling a 1 is 1/6. We're going to multiply those, and this is going to give us 1/36 for our probability. Now, we would expect the probability for 2 events to happen to be smaller than the probability for either one of these events. The probability of rolling a 5 is 1/6, or about 16.7%. So that's a 0.167. And same for rolling a 1. There's about a 16.7% chance, or 0.167 probability. And then our 1/36 is a 2.8% chance, or 0.0278. This is significantly smaller, having less than a 3% chance of having both of these things happen. That's significantly smaller than having either the 5 happen or the 1 happen the second time. That should make sense, because rolling a 5 the first time, that 16.7% chance, that has to happen before you even get to roll the second time in an attempt to roll a 1. So if you were to roll a 1, 2, 3, 4, or 6 the first time, you're already out of the game. Okay, for B, we want to find the probability of rolling an odd number the first time and a number less than 3 the second time. Well, if we look, we have, out of our 6 possible sides, we have 3 that are odd, 1, 3, and 5. So probability of rolling an odd is going to be 3 out of 6. We're going to multiply that times the probability of being less than 3. Well, the only numbers less than 3 are 1 and 2. So we have 2 options out of 6. And when we multiply, we're going to end up with 6/36, or 1/6 whenever we reduce. Remember, always reduce your fractions. For number 2, if you toss a fair coin 6 times, what's the probability of getting all heads? A fair coin simply means that there is a 50% chance it will land on heads and a 50% chance it'll land on tails. So the probability of getting all heads with 6 coin tosses. Well, the first coin toss, we have 1 out of 2 chance, or 1 out of 2 probability, that we'll get a head. Our sample space is going to be a head or a tail. So there's only 2 options, thus the 2 in our denominator. We want a head, which is only 1 of the choices out of the 2. So this is for our first flip. For our second flip, it'll also be 1 out of 2. For our third flip, also 1 out of 2, and so on and so forth down to our 6th flip. It'll also be 1 out of 2. So a half times 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 a half is the same thing as 1/2 to the 6th power, which will give us 1 out of 64. Now I want to make a note here. Whenever you're trying to repeat the same thing, so having the same outcome or the same experiment every time, if it's the same probability each time, which if you're looking for the same outcome each time it should be, then you're just going to take the probability and raise it to the power of however many times you want that to happen. So let's think of another example. Let's say we're going to roll a 6-sided die, and we want to find the probability of getting a 4 7 times in a row. So we want the probability of rolling a 4 7 times. Well, the probability of getting a 4 is just going to be 1 out of 6. The fact that we want to do it 7 times, we can take this 1/6 and raise it to the 7th power, which is going to give us quite a small number. So 1 out of 279,936, which is going to be really close to 0. So the chances of that happening are not very good. This would also be true for anything else. We could have an example where they say they give you the probability of an event happening. So for instance, if they say the probability of finishing a bottle of water, so finishing your water is a high probability, perhaps it's 0.7. And they want to know, what's the probability that somebody will finish a bottle of water 7 times in a row? Or let's do a different number. Let's make it 9 times in a row. So if we want to figure out the probability of somebody finishing their water 9 times in a row, each time they have the probability of 0.7. So we have 0.7 to the 9th power, because we're interested in this happening 9 times in a row. And that's going to give us 0.04 for our probability, so about a 4% chance. So they can either go through and give you the sample space of 1 through 6 and have you determine the probability for each. They could have you think about the sample space and come up with the probability for the event that they're mentioning, which was done in 2 and in 3, since I didn't give you a picture. Or they could just directly give you the probability of an event happening and ask you what the probability would be of this event happening multiple times in a row.